Well, now we've discussed transitions between gas and liquid. Now we're going to look at transition between solid and gas. So here we have an illustration of a block of ice. And all of these little water molecules are lined up in a very specific way. It's an ice crystal. So they're wiggling and vibrating, but about a fixed point, and so they can't move around. And so it's like the solid state of students, which you guys are in right now. You're sitting in your stools at the bench, but everybody's moving, right? Everybody is at least breathing, thankfully, but we're not moving around. But these do have kinetic energy, and the average kinetic energy is related to the temperature, but some of the molecules have higher kinetic energy than others. If you have a high kinetic energy molecule at the surface, it may be able to escape the intermolecular forces and go into the gas state. And that's a transition from solid directly to the gas without going through a liquid. And that's called sublimation. The opposite is called deposition, and that's where the gas goes directly to a solid. So these water molecules are sublimating from the solid ice, and they're going to bounce around, but then if they collide with this block of ice again, they can get trapped, and that would be the condensation. So solids also have a vapor pressure, but their vapor pressures are extremely low. Sublimation will usually happen faster in an open container where those gas particles can escape. And this is something that you can observe in your kitchen. If you go into the back of your freezer and find some ice cubes that have been sitting there for a really, really long time, they might be significantly smaller than the tray that they were made in. How does that happen? Well, the ice is sublimating. So molecules from those ice cubes are escaping into the gas state. And what do gas molecules do? They go in straight lines till they bump into something. So it escapes from the ice cube, and maybe it goes up and it hits the roof of the top of the freezer, and it might stick there, right? Or it might bounce off and hit on something else, but they're not in the ice cube anymore, and so the ice cube gets smaller.
So you were saying that they escape from the ice, though.
Mm-hmm.
So is it in general? Is it like do they tend to just like travel in a straight line, like the other ones keep them back? Like is that like they normally would they behave like a gas? Like if they weren't held back by the other? Like is that? Sorry.
No, I'm just trying. I understand your question. It's hard to put into words, isn't it?
Like is that their natural state is to just kind of go travel in a straight line with?
So, yeah, a gas will travel in a straight line until it runs into something because it's not experiencing any forces to cause it to do anything else.
Like would that be is that kind of like the natural state of a part of an individual atom, like it wasn't held together by other?
I suppose you could say that is.
Okay.
The reason that particles don't do that in the solid state is because they're stuck to each other.
There's other forces that are holding it back.
They're held together by forces of attraction between the molecules. And so they're still moving because everything has kinetic energy until you get to 0 Kelvin, absolute zero, right? At that point, the motion of the atoms would stop. But above that, we look at the desk, right? This bench, and it looks stationary, right? But all of the molecules in this bench top are wiggling, right? But they are so small, and the amount of wiggling is so small that we can't see it. But they're wiggling just like you guys are.
Is that wiggling because they want to move, but they can't because they're...
Well, they have kinetic energy, and that's motion, right? And so because they have kinetic energy, they're moving, but they're confined. When they're in a liquid, they're still trapped in the liquid, but they have more energy relative to the sticky forces, and so they're able to move past each other, partially breaking those forces, but not completely. If you completely break the forces of attraction, then it's loose and it's in the gas state. Yeah. Ice crystals will grow inside airtight bags of frozen foods. This happens a lot with tater tots. You know, you go to the store and you buy a bag of frozen tater tots because it seems like a good idea at the time, and you bring them home and you stick them in the freezer. I don't know if this happened to you. And you forget about them. And like 6 months later, and you're hungry and you're too tired to go to the store, and you find this bag of tater tots in the back of the freezer. Hey, let's cook these. So you tear open the bag and you dump it onto a pan, and there's like snow in the bag. All these ice crystals with the tater tots. What do they do that for, right? Don't they know that's just going to melt in the oven? It's going to make a mess. Everything's going to be soggy until it dries out. Why would they do that? Well, they didn't do that. That happened because you didn't use the tater tots for a really long time. And while they were in that bag, the water in the ice of the tater tots was subliming. And it was escaping, but it could only go into other parts of the bag where it got trapped and formed ice crystals. But all of that water used to be in your tater tots. So that goes on long enough, and then the food starts to become dehydrated, and we say it has freezer burn, which, you know, it wasn't burned, but it's lost a lot of the water, and so it's not very good anymore. That happens a lot with meat. You know, you throw a piece of steak or something in a Ziploc bag and toss it in the freezer, and you come back a while later, and it doesn't look the same, right? Because there's all these ice crystals in the bag, and the meat is kind of dried out on the edges and not very good anymore. Well, how do you avoid that? Well, you can spend a lot of money and get a deep freeze, which is colder than a regular freezer, because the colder it is, the less sublimation will happen. Or you can do a better job of sealing up your food. You can seal your food without any airspace so that there's less opportunity for those water molecules to sublime. Because if they start to break free, they can't really go anywhere, and so they just go back down where they came from.
You vacuum sealed it?
Yeah, like a vacuum sealer. And you can buy, you know, vacuum sealing machines and fancy bags. And a cheap way to do that is to use a Ziploc bag and a straw, right? So you mostly seal the top of the Ziploc bag, and you stick the straw in there, and you hold it tight, and you suck all the air out, and then you seal it. And so you can get close to the same effect without buying an expensive machine.
How do you seal it after you've sucked the air out? How do you?
Well, you have to be quick about it.
Okay.
Yeah, you have to have your hand ready and just pull the straw out and squish it. It's not perfect, but it's better than just throwing it in a bag. Or it always cracks me up with small children. Put that in the freezer, and they'll just put a piece of food in the freezer without any wrapping or anything. Put your sandwich in the fridge, and they just set it on the shelf. I'm like, a little more explaining is needed there. Okay, dry ice. Dry ice is solid carbon dioxide. Why do they call it dry ice?
Because it doesn't melt.
Because it doesn't melt. Regular ice in the cooler will melt, and if you have food in there like sandwiches, they get all soggy, right, and nasty. Dry ice doesn't do that. Dry ice is really useful if you're shipping things that need to be refrigerated, because postal service and other delivery services really don't like when liquids are coming out of packages, right? If the ice is melting in your package and it's dripping all over the place, they're like, well, I hope that's water, but I don't know, and they get really uptight about it. So dry ice is often used for shipping things.
Can it ever melt? Sorry.
It cannot melt at normal pressure.
Okay.
It never does.
But if
Yeah.
you change the pressure, it could.
Yeah. So that's a piece of dry ice. And what looks like kind of a cloud coming out of it, you can't see the carbon dioxide that's coming off of it, but it's very cold, right? And so as the carbon dioxide gas comes off of it, it's very cold, and because it's so cold, the water vapor in the air condenses and forms this little cloud. Okay, fusion. Fusion is another word for melting. So that's going from a solid to a liquid. So if we take a piece of ice, maybe at negative 10 degrees, and we add heat to it, the particles are going to vibrate more and more and more until we get to the melting point, at which point they have enough thermal energy to partially overcome those intermolecular forces, and now they can slide around and it becomes a liquid. The temperature will not increase until all of the solid has melted. So that's very much like what happens at the boiling point. The temperature doesn't go up until the state change finishes. After everything's melted, then the temperature can go up. So melting and fusion are the same thing. The opposite of melting is freezing, going from a liquid to a solid. If you have a mixture of ice and water, that's going to be at 0 degrees Celsius, or very close to it. You know, is the atmospheric pressure exactly 1 atmosphere? Is your water really pure? It's going to be very close. And the temperature won't go up until the ice melts, and then the temperature will go up. So melting is an endothermic process. How do you get an ice cube to melt? You heat it up, right? This is called the heat of fusion. So that's why we have to use the word fusion instead of just melting, because heat of melting, I guess, just sounds dumb. I don't know. So how do you remember that fusion is melting? I think about chocolate chips. What happens as you heat up chocolate chips? They get soft and they start to fuse together, right? Fusion. So the heat of fusion is the amount of heat needed to melt 1 mole of a solid. So for water, that's 6.02 kilojoules per mole. Melting is endothermic. That means freezing is exothermic. When water freezes, it gives off heat. That seems weird, huh? So I live in Reedley, which is, a fruit basket of the world. That's what the sign says anyway. But we got like all kinds of fruit trees and stuff, a lot of citrus. And in the winter, we sometimes get freezing temperatures. And if you get down to like 26 degrees Fahrenheit for more than a couple of hours, then oranges can begin to freeze, and that causes their cells to break and they're ruined, right? And then you've got this whole economic crisis because the orange crop froze. How do you keep the fields warm so the oranges don't freeze? Well, you can't build tents around them and put big heaters in them. But you can use this freezing is exothermic idea. So what they'll do is they'll water the fields, they'll flood the fields so they're just like super, super wet. As the temperature of the air drops, the water begins to freeze. But look what happens over here. As the temperature drops, the water begins to freeze. The temperature will not go down any further until all of it has frozen. So as the water is freezing, it is releasing energy that keeps everything around it at 32 degrees Celsius. It's Fahrenheit. And it won't go down below that until all of it has frozen. So then you also throw some wind machines in there to blow that slightly warmer air around, and you can keep the citrus crop from being ruined. Heats of fusion are usually a lot smaller than heats of vaporization, because in order to melt something, you don't have to completely break all the intermolecular forces. You just have to partially overcome them.